Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the concept illustration problems to understand the concept of gravitational potential as well as that gravitational potential energy. So in this first problem, you can see that there is a system of three masses which are placed on the vertex of equilateral triangle of side A. We have to find out the potential energy of this system. So the method 1 is a very simple method in which and it is the recommended method in which we would use the direct formula, and we know that the gravitational potential energy is minus gm1 m2 by r, and therefore we have to count the different number of pairs. So you can see that this is one pair, this is one pair, and this is one pair. So there are three number of pairs. So the total gravitational potential energy would be minus g m square by r. In fact, the distance between any of the two masses is a, and minus g m square by a and minus g m square by a. So u would be equal to minus 3g m square by a. This is the potential energy of this system. Now we can also use a second method to conceptually understand the potential energy. We have already defined that potential energy is the amount of work done in assembling this system slowly from infinity. So let us assemble this system one by one from infinity. So let us see that initially there was no mass here, and we brought a mass m from infinity at this point. So you know that when we are bringing this mass m from infinity, then there is no gravitational field present in this region to pull this mass. Therefore, in order to bring this mass with constant velocity, we would not apply any force because there is no attractive force. So we would not apply any another force to cancel that force. So there is no force applied by us, and therefore the work done in bringing this mass W1 will be 0. So W1 will be 0. Now after bringing this mass, we brought another mass m from infinity at this point, and the work done by us is W2. Now we know that we have brought this mass after bringing this mass. So at this point, this mass would create some gravitational potential. So we have to do some work against the gravitational pull of this mass. So the work done, W2, would be equal to m into v, or m delta v, where m is the mass which we are bringing from infinity, and delta v is the potential difference between those 2 points from which we started and to which we ended. So the work done, W2, will be equal to m into v. Now v of this point would be obviously due to this mass only. So this would be minus gm by a, and voltage of infinity, potential of infinity, would be 0. So work done, W2, would be equal to minus gm square by a. And now we bring the third mass here. W3 is the work done in bringing this third mass. So W3 will be equal to m delta v again, where m is the mass which we are bringing and delta v is the potential difference between the final and initial point. So this is the final point at which we are bringing this mass, and the potential at this point would be due to this mass and this mass. So the potential would be minus 2 gm by a, because due to this mass the potential would be gm by a minus gm by a, and due to this mass the potential would be minus gm by a. So the total potential would be minus 2 gm by a, and the work done 3 would be equal to minus 2 gm square by a. Now we know that the sum of these three work dones, W1 plus W2 plus W3, would be the potential energy of the system, and hence you can see that the potential energy would be minus 3 gm square by a. This is the potential energy of this system, and we can check this value with the previous one. So obviously in numericals we would use this approach, but this approach was just to justify the definition of the potential energy, that it is the work done in assembling these constituent masses in form of this triangle from infinity slowly by the external force. Now let us move on the concept illustration problem 2. In this problem you can see that there are two figures. First figure you can see is a triangle, and the second figure you can see is the square. So we have to rearrange the four masses. You can see the four masses. 3 are kept at vertex and 1 is kept at centroid. So we have to rearrange these four masses in form of a square of side A from the triangle of side A. So what we will do, that we know that the potential energy of this system is, let's suppose, U triangle, and the potential energy of this system is, let's suppose, U square. So the work done in rearranging them would be U final minus U initial. So obviously in the case of this square you can see that there are 6 pairs. This is 1, this is 2, this is 3, this is 4, and this is 5, and this is 6. So for 4 pairs, let us find out the potential energy of this square system. So this would be minus 4 gm square by a for these 4 pairs, and minus 2 gm square by root 2a, because this distance is root 2a. This is root 2a. Okay. Now, so u square would be equal to u square would be equal to minus 4 gm square by a, and minus, this is root 2 gm square by a, and u of triangle would be equal to, there are also 6 pairs in this case, 1, 2, 3, 4, 5, 6. So u of triangle will be equal to a minus of 3 gm square by a, because in this pair the distance between the two masses is a, and in this pair the distance between the two masses is a by root 3. You know that this side length is a by root 3 and this is a by 2 root 3. So this would be minus of 3 gm square by a by root 3. So u of triangle would be minus gm square by a into 3 and minus 3 root 3 gm square by a. Now we know that the work done would be equal to u of a square minus u of triangle. So this work done would be equal to, taking out common, gm square by a with a negative sign, and the work done would be equal to u of a square minus u of, in fact let us take out the plus gm square by a. So u of a square would be 4 minus 4 minus root 2, and u of triangle would be plus 3 root 3. Here there is a positive sign. It is due to the fact that when we will subtract u of triangle from u of a square, then this negative would become positive. So work done would be equal to gm square by a into 3 plus 3 root 3 minus 4 minus root 2. This is the work done in rearranging that system into square. Now let us move on another concept illustration problem that you can see that there is a equilateral triangle and there are three masses of equal mass m which are placed on the vertex of this triangle, and there is a mass m which we are bringing from infinity to this point centroid. So we have to find out the work done in bringing this mass slowly from infinity to this centroid point. So we know, again we are discussing the two methods to solve this problem. So method 1, which is the recommended method, will be the method of work done, calculating the work done by formula m delta v. This is the best method which we can use, and we can use to calculate these type of questions in the quickest time. Now we know that the mass m is the mass which we are bringing, and delta v is the potential difference between the final point and initial point. So final point is centroid and initial point is infinity. So work done will be m into VO. Now we know that the potential at this point would be created by these three masses, obviously, and the individual potential of these three masses at this point would be same. So the total potential at this point would be the sum of the individual potentials of these three masses, and therefore it would be minus 3 gm by a by root 3, because this is a by root 3. Okay, minus the potential of infinity is 0. So work done would be equal to minus 3 root 3 gm square by a. This is the work done in bringing this mass from infinity slowly to this point O. Now let us discuss the second method to solve this kind of problem. In this second method, we would just use the formula that work done would be equal to the change in potential energy, U final minus U initial. Okay, so the additional, let's suppose that the system, initially this system was in this form, in which only three masses were placed on the vertex of equilateral triangle, and finally when we brought fourth mass from infinity to this point, then this system becomes like that. So we, if we have done some additional amount of work done in bringing this mass, then that work done would be stored in this system in the form of potential energy, and due to which this the potential energy of this system would be greater than initial potential energy. So if we need to find out the work done by us in bringing this mass from infinity to this point, then we can just find out the difference between this final potential energy and this initial potential energy. So obviously the initial potential energy would be calculated by analyzing the pairs. So there are three pairs in this case, so the potential energy would be minus gm square by a, and in this case there are 6 pairs. So the potential energy of these three pairs would be minus gm square by a, and the potential energy of these three pairs would be minus of 3 gm square by a by root 3. So U final would be equal to minus of g, in fact there would be a 3 also here, and there is a 3 here also, so this is minus 3. So this is minus 3 gm square by a, and this is minus 3 root 3 gm square by a. So the work done by us would be the final potential energy minus initial potential energy, and it would be 3 root 3 with a negative sign gm square over a. So this is the work done, which we have already calculated by the method 1. Now again you can see The method 1 is the shortest one, and therefore it is highly recommended to use this method to calculate such type of work done. Now let us move on the another concept illustration problem. Now you can see that in this problem there is a mass m which was released from rest from this position, which is at a distance of r from this fixed mass m, and obviously this mass will attract this mass, and at a moment later they would be at a distance of r by 2 from each other. So at this moment we have to find out the velocity of this mass. So what concept would we use? We would use the law of conservation of total mechanical energy. We know that the total mechanical energy, this is total mechanical energy, is the sum of kinetic energy and potential energy. And it remains constant when there is no external force acting on the system, as well as all the internal forces are conservative in nature. So obviously here the gravitational force is the only force acting between these two masses, which is the internal force of this system. Therefore there is no external force acting on the system, as well as the internal force, which is the gravitational force, is a conservative force. So we can use the conservation of total mechanical energy. Now initially you can see in this initial case the kinetic energy of the system initially was 0, and the potential energy of the system was minus gm square by r. And finally the kinetic energy would be half mv square, and the potential energy would be minus 2gm square by r. Why I am using this 2 is due to the fact that in the denominator there would be r by 2, so 2 would be here. Now we know that the kinetic energy has increased, so the gain in kinetic energy, obviously the gain in kinetic energy would be due to the loss in potential energy. So we are just equating the gain of kinetic energy to the loss of potential energy. So the gain in kinetic energy is let us use different page. So the gain in kinetic energy is equal to half mv square, and the loss in potential. Now when we are referring the loss in potential energy, then it automatically is understood that the potential energy has decreased. So the initial potential energy would be greater, so we would find out the loss in potential by subtracting the final potential energy from initial potential energy, like that. So U loss would be equal to, U initial was minus gm square by r, and U final was minus 2gm square by r. So U loss will be equal to gm square by r. Okay, so this loss in potential energy is equal to half mv square, and by this you can find out v, which is under root of 2gm by r. This is the velocity with which this mass will approach this fixed mass at a distance of r by 2 instantaneously. Now in the second case, you can see that if this mass is not fixed and it is free to move, and the mass of this mass is 2m and the mass of this mass is m, then we can easily understand the situation that both of these masses would move, obviously, because they both are pulling each other. So let us see that there is no external force, so we can also balance the momentum. And initially both masses were at rest because they were held at rest by some force, and when we release them, then at some instant of time they would be moving towards each other with velocity v1 and v2. The initial instantaneous distance between these two masses was r, and this final instantaneous distance between these two masses is r by 2. So what we need to find out, we need to find out the velocities v1 and v2. So in the initial case, you can see that the kinetic energy initially was 0, and the potential energy initially was minus 2g. In fact, I would write it here. So the potential energy initially was minus 2 gm square by r, and in the final case, this case, the kinetic energy is half mv1 square plus half into 2m v2 square, because the mass 2m is moving with the velocity of v2. And the potential energy in the final case would be equal to 4 minus of 4 gm square by r. So again, we would use the same situation, that the gain in kinetic will be equal to the loss in potential. So the equation will be that half m v1 square plus half 2m v2 square, half m v1 square plus half 2m v2 square will be equal to the loss in potential. So when we are referring the loss in potential, then by default we are referring that initial potential energy would be higher and final would be lower. So the difference of these two potential energy would be u initial minus u final. So this is u initial minus u final. So this is mv1 square by 2 plus this is mv2 square, and this is equal to u initial is minus 2gm square by r minus of minus 4gm square by r. So mv1 square by 2 plus mv2 square is equal to minus of this would be plus of gm square by r into 2. Okay, so this is the first equation, but you can see that there are two variables, v1 and v2. So now we would use the momentum conservation to find out these two variables. So initial momentum was 0, and finally the momentum was mv1 minus 2mv2, because this mass was moving in this direction and this mass was moving in this direction. So the momentum of the system would be mv1 minus 2mv2, and we have to equate it to 0 because initial and final momentum would be equal, because there is no external force acting on the system. So we can say that mv1 is equal to 2mv2, cancelling this m with m. This v1 is equal to 2v2. So now we can use this v1 is equal to 2v2 and we can substitute the value of v1 here. So let us term it as first equation, which we have already done. So substituting v1 here, so it would be 4v2 square by 2. So it is 2v2 square plus v2 square. Okay, what I have done, that I have substituted the value of v1 here. So it would be 4v2 square by 2, and 4 by 2 is 2. So plus v2 square is equal to 2gm by r. This is 2gm by r. Okay, so this is 3v2 square is equal to 2gm by r, and therefore v2 is equal to under root of 2 by 3 gm by r, or we can write it as 2gm by 3r. And obviously v1 would be equal to twice of v2, so it is 2 of under root of 2gm by 3r. So these are the values of v1 and v2. Now let us move on the next concept illustration problem. This one. So in this case, you can see that there is a system in which there are four masses m, m, m and m, which are initially placed on the vertex of the square which has a side of a. and when we will release these masses from rest, then they would start to move in the direction which is along the diagonal, because each of them would be pulling the other mass. Like we talk about this mass, so this mass would be pulling this mass in this direction, this would be pulling in this direction, and this would be pulling in this direction. So the resultant force on this mass would be in this direction. Similarly, the resultant force on any of the mass would be along the diagonal, and when we will release them from rest, then they would start to move along the diagonal only, like that. So now there would be a situation in which these masses would again be forming a square, and the side of the square would be a by 2, and these masses would be having some kinetic energy or some speed at this time, or and this speed of these all four masses would be same, obviously, because the system is symmetric and each of them is experiencing the same amount of force on it. So we have to find out this speed. So we know that again we will use the fact that the gain in kinetic would be equal to the loss in potential. So the gain in kinetic would be initial kinetic energy would be 0. So in this case the final kinetic energy is 4 times of half mv square. Okay, and the loss in potential would be the initial potential energy minus final potential energy. So this is 2 mv square, and this is equal to the initial potential energy was there is, you can see that there is there are 6 pairs, 1 2 3 4 and 5 6. So let us find out the initial potential energy. So it was minus of 4 gm square by a for these 4 pairs, and for the other 2 pairs it is minus of 2 gm square by this distance is a by root 2, in fact root 2a. This complete distance is root 2a. So u initial would be minus gm square by a 4 plus root 2, and u final would be obviously different due to the fact that this side a has become a by 2 now. So u final would be minus 2 gm square by a, and this is 4 plus root 2. So the u initial minus u final would be gm square by a into 4 plus root 2. Okay, so cancelling this m with m, we can see that v will be equal to under root of gm by 2a, and this is 4 plus root 2. So this is the value of speed with which they would be moving in this at this instant of time. Now this was all, and this was the concept illustration problems to illustrate the working of or the applications of potential energy and the potential. I hope you are having more clearer picture now about the potential energy and potential. Keep tuned. We'll be bringing some more important concepts of gravitation in the next video. Thank you.